So in this video, what we're going to do is state, and in the next video, we'll prove the theorem that allows us to give recursive definitions. In other words, why are we able to recursively define sequences or functions in set theory? We kind of cheated a few videos ago when we proved this characterization of what it meant for a set to be a well-ordering. Remember, our set's well-ordered if and only if there's no infinite descending sequences. And in one of the directions, namely the one where we assumed our set wasn't well-ordered and constructed an infinite descending sequence, we constructed the sequence by recursion, or we constructed it recursively. And why this theorem is going to be the justification for why we were able to do that. But it's more general because that was just recursion on the natural numbers, but this works for any well-ordered set. What we'll need first is a definition. So a function, or f is a partial function. F is a partial function. A partial function. From A to B. Well, what would it mean to be a partial function from A to B? Well, you are a function, but your domain might not be all of A. It's just going to be some subset of A. So if there's some subset A prime such that f is actually a function from A prime into B. And the way that we might denote that, we might denote this f is a partial function from A to B. We'll write the right arrow, but with only the top hook, I guess. So f is a partial function from A to B. Well, if it's a function whose domain, if its domain is some subset of A, and if we were to kind of maybe think of the graph of something like this, let's say that we could graph it, what would it look like? Let's say that A was right here, and this was B. Let's say that A prime was this green stuff right here. Maybe our partial function looks something like this. Okay, I guess this fails the vertical line test, but let's pretend that it didn't. So this might be a partial function from A to B. So that is what a partial function is. What is going to be the statement of the result? We're going to prove. Here's our theorem. This is going to be for recursive definitions. So here's the statement. Let A be a well-ordering. Be some set. And let's assume that f is a function from A times P into B. Now, I didn't say what P was. So we have a well-ordering, a set B, and this function big F, where what's P? P is going to be all partial functions from A to B. All partial functions. From A to B. Okay, now what just happened? What is F supposed to be? Well, big F is supposed to be the rule that we use to kind of generate our recursive sequence or function. So if we're defining something recursively, we normally have a rule that tells us if we're given all the previous terms, how do we get the next one? This big F is supposed to be representing what that rule is. So this is supposed to be the rule. Big F is the rule. And then what's the conclusion of this theorem? then there's a unique function big G. A unique function big G. And this is going to be a function from all of A to B, such that what is true? Well, such that for every single value y in our well-ordered set A, well, G is supposed to tell us what we're supposed to be able to figure out what G of y is. Well, this is supposed to be the yth recursively defined element. How do we figure out what that is? Well, we're going to have it's going to be what the rule tells us to do when we have access to all the previous elements. So this is going to be what our rule f tells us to do when we have access to y, right? If we're plugging in y, we should be able to use it as a parameter. And what's our partial function? Our partial function is going to be G restricted to all of the previously defined values. So it's G restricted to all the predecessors of y. All right, so let's say that again. So we have our big F, that's our rule. And what the domain of our rule is going to be our set A, because if we're plugging in, if we're trying to figure out, say, what the 20th recursive element in our recursive sequence is, we should be able to use 20 as a parameter. And this set of partial functions here from A to B, that's supposed to represent all of the previously defined information. And what's the conclusion is that there's a unique function big G, such that if I plug in any value in A, so y, so if I want to figure out what G of y is, its output is going to be what the rule told us to do, assuming that we had access to all of the previous information. So this is our parameter y. You can think of this as a parameter. And what is this? This is encoding all of the previously defined values. So just remember, if you have a function and this notation here means that we're taking the function and we're restricting the domain to this set here. So I'll write it over here. So G restricted to this set. Well, this is the function G with domain this set here. And why is this function G in our set P, right? The right coordinates here are supposed to be in P. Well, we're assuming that we have this function G already. And if we have this function G, it's a function from A to B. So if we restrict the domain to any subset of A, it's going to be a partial function from A to B. Okay, so that's the statement of the theorem. This is, when I saw this for the first time, I knew what recursion was, and I knew how to kind of give recursive definitions, but for some reason I thought this is, I found this kind of really technical. So let's maybe give an example. Before we give the proof, let's give an example of, say, how to recursively, let's define the Fibonacci numbers recursively. And let's do it in such a way where we kind of are making the setup look like the hypothesis of this theorem, and see what happens. So we're going to give an example. Let's define the Fibonacci numbers. So what's the setup? Well, we need to say what our well-ordered set is, and in this case it's going to be omega with the membership relation. And remember, well, omega is just the natural numbers, so we can kind of really just think about this. This is just the natural numbers with the less than ordering. And so in the statement of our theorem, we needed our set A, but we also needed the set B. And the set B is going to be, it's going to be omega union this extra set. We'll just call it error. So what is this term? This is just any set that's not in that's not an omega. Now remember, in the hypothesis of this statement of our recursion theorem, we have this function big F from a times p into b. And what's about to happen is, or why do we need this error term? Well, p is all partial functions from a to b, and in this case is going to be all partial functions from omega into this set b, omega union this additional error set. Well, if we're going to give a recursive definition, we don't need access to all the partial functions. We just need access to the partial function of the previously defined information. So this function f is going to give us a lot of unnecessary information. And so what we're going to, when we give this definition of our rule, we're going to have to say what we do when we kind of, our two inputs are either incomprehensible, or it doesn't make sense, or just if something crazy happens as an input, we just want to output error. We don't want to think very hard about it. So what's going to be the definition of this f? So we're going to try to define the Fibonacci numbers. Well, f is going to take two inputs. It's going to input a natural number and a partial function. And what's the output going to be? Well, it's going to depend on, it's going to be a definition by cases. Well, if n was 0, then what we're going to output is 0. So if n is 0. And if n was 1, then we're going to output 1. Those are the first two numbers in the Fibonacci sequence. And what's going to happen when n is bigger than or equal to 2? We're going to output the sum of the previous two values. And in this case, we're going to, g is supposed to be representing all of the previously defined values. So what we're going to do is we're going to output gn minus 1 plus gn minus 2. If what happens? Well, if n has to be bigger than or equal to 2, g can be any partial function. So we just want to make sure that if we're doing this, we want to make sure that n minus 1 and n minus 2 are both in the domain of g. So n minus 1 is in the domain of g, and n minus 2 is in the domain of g. And the other thing that we need is that gn minus 1 and gn minus 2, they shouldn't be the error term. So let's say that if, so again, p can be any, it's going to be the set of all partial functions from a to b. So maybe g would have, maybe n minus 1 and n minus 2 are both in the domain of our function g, but maybe the output was the error term. And if that was the case, what we're going to do is we just want to make sure in this case that gn minus 1 and gn minus 2 are not both the error term. So they're both not the error term. So gn minus 1 is not equal to error, and gn minus 2 is not equal to error. If we're in a situation like that, then, well, this definition makes sense. Gn minus 1 and gn minus 2 are both going to be natural numbers, and we're going to be able to just add them up. And what we'll do otherwise is, if we're not in any of these cases, we're just going to output error. So we're an output error otherwise. Okay, so what does this theorem tell us? This theorem tells us, so the recursion theorem, what it's going to give us, theorem, it gives a unique function g and this is going to be from omega into omega union the error term, such that for each natural number, well, g of n is going to be f of n, and then what's going to be our partial function? It's going to be g restricted to all of the natural numbers that come before it. So this is what the conclusion is of our recursion of this theorem. Now, there are some things that you can actually show by induction. If you did an induction on n, so by induction on n, you can show that this function g is actually never going to output error. So you can show that gn is never equal to is never equal to error. So you can just show that by induction on n, and well, if you kind of unravel what all of this is saying, what we're going to get is the following. So g of n is going to be equal to, well, it's going to be equal to 0 if n is equal to 0. It's going to be equal to 1 if n is equal to 1. And if n is bigger than or equal to 2, what we're going to get is we're going to get g of n minus 1 plus g of n minus 2. If n is bigger than or... And so, okay, so that's what this theorem is giving us at the end of the day. Now, how do we actually compute this in practice? In practice, what we're going to do is we're not really computing all of g at once. We're just computing kind of these like approximations of what g are. So in practice, we don't actually compute g, we compute approximations of g. Maybe we'll put some more space down. In practice, we don't compute all of g at once. Instead, we compute approximations of g. Approximations of g. So what do I mean by that? So in our Fibonacci example, well, if we want to figure out, I guess, what our first approximation is, so what we get when we plug in 0, well, that's just going to be, say, 0. If we want to figure out what the next approximation is, well, we're going to have access to 0 already, and then we want to input 1, and we know we're going to get 1. What about for the next approximation? We have access to the previous two values, and what we're going to get to the next one is we're going to add the previous two values together. So we're going to get 1 again. What about for the, I guess, the fourth approximation? We're going to have access to all the previous values, and to get the next one, we're going to add the two values. What I'm trying to get at here is that we're not actually ever following this procedure. We're kind of defining g, but we're defining g by just kind of defining a bunch of approximations of what g is. And if we say wanted to figure out what the 400th, what we get when we plug in 400 into g, we're computing the first 400 approximations of this thing, and then using that to figure out what the next value is. So we can think of all of these things as partial functions. So this is maybe what I'll stop at in this video, and then we'll give the formal proof the next time. But all of these are partial functions. So each gn is a partial function. From, well, in this case, it's going to be from omega to omega, but generally it's from omega into b. And what's going to be the, all of these are approximations of our function big G. How are we going to use all these, what we're going to prove next time is that there's always these approximations of our function G, and then what's going to be the function G that we care about? It's actually going to be the union of all of these GNs. So next time, what's the idea of the proof? The idea of the proof is that our function G is actually just the union of all of these values. And just to kind of digest what this means, what is a function kind of set theoretically? It's a set of ordered pairs. And these are all sets of ordered pairs. We could union them all together, and because they're kind of coherent, right? The input for all of these partial functions, say when we look at the value at if we plug in 0 into any of these partial functions, we're always going to get 0. If we input 2 into any of the approximations after G0 and G1, we're always going to get 1. These kind of functions are all extensions of each other. So if we take the union of all of them, we're going to get a new function, and we're going to show that the domain of this new function is going to be all of A, and that's going to be exactly what our function. And I guess we'll have to do some more stuff to make sure it all works out. But this is going to be exactly our function G that we were searching for in I guess from the start.